latent heat, which we've talked about a little bit already, but not in terms of the kind of the math of it, but just in terms of what it is, okay, is also pretty easy. Okay, remember that latent heat we talked about before is the energy that it's kind of like potential energy, right? If we're talking about mechanical energy, there's kinetic energy, energy when it's moving, and there's potential energy due to its position above the ground. It's the same for thermal energy. Okay? When we're talking about thermal energy, we measure the kinetic thermal energy of a material with its temperature. Okay? Temperature essentially is kind of a measure of how fast the particles in a substance are moving. Okay? We measure that with a thermometer, and the way a thermometer works, okay, really at its most basic level, okay, a thermometer has a bulb at the bottom, right, and it's got the alcohol inside, and really what it measures is how many times the bottom of the thermometer is struck by moving particles. Because every time a small atom strikes the thermometer, it transfers energy to the thermometer. Okay? It transfers thermal energy to the thermometer, and the thermometer's material, the alcohol inside, expands and takes up more space. Everyone follow me there? Okay? So materials can have kinetic thermal energy that is measured by temperature. However, if we also, not so much, however, also, okay, materials can change state. If we're looking at water, water's an easy one because it changes state within a fairly narrow temperature range that we're familiar with. If water is below zero, it's a solid that we call ice. Okay? When water is a solid, the particles are close together. Okay? And when they try to move, they run into each other, okay? And they transfer energy to each other by conduction. But the particles are really close together. If I add energy to the ice, what will happen to it? If I heat it up, what will happen to it? It'll melt. Yeah, first it'll heat up to zero, and then it'll melt. Okay? Once it starts to melt, what happens to the space between the particles? It gets bigger, right? They spread out when they become a liquid. Okay? Does that mean now that it has more potential energy than it did when the particles were right here? Yeah, because it takes energy to melt ice. Okay? In fact, it takes energy to turn anything from its solid form into its liquid form. A change of state requires a lot of energy, in fact, way more in general than it requires to change the temperature of a material. Okay? Because we're changing the thermal potential energy of that product. Now, if I keep heating the water, eventually the water is going to turn into steam. Okay? It's going to turn into a gas. Right? And when it turns into a gas, what happens again to the space between the particles? It spreads out even more. Okay? So now they have even more potential energy or latent heat. Okay? When all that water vapor, as we were talking about the other day, moves to a new area and condenses, the particles move from being this far apart to being this far apart. And they release all of that energy that they absorbed in changing state back into the environment. That's what we're going to look at here with this graph. This is the heating curve of water. Okay? And it shows us the different types of energy changes that are going to go on as I heat up a block of ice. Okay? So if I have a block of ice at minus 25 degrees Celsius and I start adding heat to it, it doesn't melt right away. Okay? It heats up until at least part of it is what temperature? Zero. Because ice doesn't melt until it gets to zero. If we're talking about ice made from distilled water, right? Obviously, if there are impurities in the water, that can change its melting point, and we do that on purpose. Okay, we talked about adding salt to the roads to make the ice melt at a lower temperature. Okay, if you add antifreeze to something, okay, then the antifreeze changes the nature of the water, and it freezes at a lower temperature. Things like that, like especially with washer fluid, right? When it starts to, on your car, right? You pull the little handle in your car and sprays the windshield wiper fluid on there. You got to make sure you put the blue stuff in there, because if you don't, what'll happen? It'll freeze solid, and that's bad because it'll also break the container, the reservoir that stuff is stored in. Because what does water do when it freezes? It expands, yeah. Okay, and you see that all the time in rental vehicles. Okay, you get a rental vehicle and you pull the thing for the squirter and it doesn't squirt. You open the hood and there's pieces of plastic everywhere. Okay, where the reservoir is supposed to be. So always make sure you put the blue gunk in that. Don't just fill it with water. In the summer you might get away with that, but just don't forget you did it. Okay, it comes to be like November and you forgot you did that, you're in trouble. Okay, back to this. Sorry, that's how my mind works. All right, so we get the ice up to 0 degrees Celsius by adding energy. When we're taking it from minus 25 to 0, what kind of energy about the ice are we changing, kinetic or potential? Remember, we said temperature, when I drew the thermometer there, is a measure of the kinetic energy of a material. So if I'm changing the temperature, I'm changing the kinetic thermal energy of the material. All right, do we have a formula that allows us to calculate the amount of energy required to make a kinetic thermal energy change? Spoiler alert, you've been using it all morning. What is it? Well, that's scary. You've been using this formula all morning, guys. E equals mc delta T. Okay, is this calculating energy? And is it using change in temperature? Okay, anytime we're talking about change in temperature going with energy, we're talking about kinetic thermal energy. Okay, so I can calculate how much energy would be required to change the temperature of a block of ice as long as I knew its mass from minus 25 to 0. That's what we're going to look at today a little bit. Okay, once I get it to 0 degrees Celsius, something weird happens. I keep adding heat, and the temperature stops changing. And it won't change again until all of the ice is melted. That's why we put ice in drinks. Okay? When you put ice in drinks, yes, the ice is cold, but once you put it in the drink, its temperature very rapidly gets to 0 degrees Celsius. Okay? But then it stays there. And the temperature of your drink continues to go down because where's the energy going? Yeah, it's going into the ice, not to change the ice's temperature, but to change the ice's state. Okay? As ice melts, it can absorb a lot of energy, and that keeps your drink cold for a decent amount of time, depending on how much ice you put in it. All right? Everyone follow me on that? Now, if you wait too long, obviously your drink is diluted by the time you drink it because the ice is completely melted. Right? But ice does a very good job of keeping things cold, right? Because it can absorb lots of energy while changing state. Okay? That's why we fill coolers with it. You know, if you're going camping, you got all your food in there, you want to make sure it doesn't spoil, you just throw a bunch of ice in with it, and for days even, that cooler stays cold because the ice just keeps absorbing energy from the food, keeping everything in that cooler at 0 degrees or around 0 degrees Celsius. Okay? All right, so I keep adding energy, temperature doesn't change, but I get the ice to melt. Okay? Once all of the ice is melted, if I keep adding heat, what's going to happen? It's going to get to boiling. Yeah, the temperature is going to increase. Okay, and that's what we see on this graph. Okay, if you look at the axes here, the bottom is how much heat I've added, and this is temperature on this side. Okay, so I keep adding heat along the x-axis. If I keep adding heat, the temperature of the water goes up. And you can see it goes up pretty quickly. It doesn't take much to get the temperature from 0 to 100. All right, now at 100 degrees Celsius, same thing's going to happen. I'm going to keep adding heat, but the temperature is not going to change. Liquid water simply doesn't exist above 100 degrees Celsius, but it takes quite a while to change liquid water into water vapor. Look at how much energy has to be added on that graph. That's the longest part of the graph. Okay? That's why water vapor moving from one place to another can carry so much energy, and it's such a big part of energy transfers in our global system. Okay? It carries all of this energy with it, okay, everywhere it goes, and then when it gets there, it releases all of that energy as it condenses back. All right, so I keep adding energy, and I eventually get all the water to evaporate. Okay, so now I've got a container full of 100 degrees Celsius steam, and I keep adding heat to it. What happens to the steam? If I keep heating the steam's going to get hotter. Yeah. Okay. And I keep heating steam, it'll just get hotter and hotter and hotter until I can't remember what the temperature is, but eventually it'll start to degrade and become plasma. We don't deal with that. That's a totally different part of the graph. Okay, right? Because it kind of ceases to be water once it becomes plasma, so we don't deal with that part. But if I keep heating it, the steam keeps getting hotter. Okay, so again, this part here would be a kinetic energy change. this part here would be a kinetic energy change. Same with this part. So if I wanted to calculate the energy here, here, or here, which formula do I use? This one. Okay, because I have a change in temperature happening, I would know the mass of the material, and I know what it is. So I could calculate the amount of energy needed. Everybody with me there? All right, so that tells us 3 of the 5 sections of the graph, how we would calculate them. I need to know how much energy is required to melt ice, and this big part, I need to know how much energy is required to vaporize water. Okay? Does this graph also go in reverse? Yeah. Just when I calculate the energy, it would be not the energy required to do it, but the energy that would be given off. Okay, so if I started up here with steam and I put it in a fridge, the fridge would absorb all of this energy, and then it would absorb all the energy while it condensed back down into water, and then it would absorb all this. The numbers are the same, the method is the same. You would just write released instead of required, okay, in that case. All right, so let's look at the math of latent heats now. All right, there's 2 kinds of latent heat. The kind of latent heat that deals with this part of the graph, where we melt something or it freezes, okay? And the kind of latent heat that deals with vaporization or condensation, depending on which way you're going, okay? Those are the specific latent heat of fusion and the specific latent heat of vaporization. Okay, so the specific latent heat of fusion deals with the state change from solid to liquid or liquid to solid. Okay, it deals with the melting and freezing. Right? The specific latent heat of vaporization deals with vaporization and condensation, depending again on which way you're going. Okay, we're only ever going to deal with water when we're talking about latent heat, okay? Because most other substances don't have a lot of state changes within the temperature range we could deal with. Okay? All right. Yesterday we said that the specific heat capacity of water was 4.2 joules per gram degree Celsius. Right? So to change the temperature of liquid water by 1 degree Celsius, for each gram will require 4.2 joules. Okay? To melt 1 gram of ice and turn it into water, requires 333 joules. Is that a lot more? Yes, it is. Okay? Have you ever made snowball with your bare hands? How do your hands feel after? Numb, cold. Why? Because the energy that's required to melt the ice when you're making the snowball is coming from where? From you. For every gram of water, of every gram of snow that melts in your hand, you lose 333 joules of energy to do it. Okay? Your hands get cold in a hurry at that rate. Okay? That's why it's so difficult and why your hands get all red and stiff. Okay? Because they're losing energy like crazy. Right? Or if you get that, you're having a snowball fight and some snow goes down your back, okay, while you're having, and you just get that chill immediately, because there's probably a couple of grams worth of snow that went down there and it melted right away, okay, and you lost 600 and some, okay, joules worth of energy just like that. All right, everybody follow there. Okay, so it's a lot of energy, right? Okay, up here where we're boiling and condensing. Okay, 333 joules to melt something, but to vaporize that same single gram of water, 2,760 joules. That's a lot. That's why that part of the graph is the longest. Okay? We're talking about an incredible amount of energy required to evaporate water. Right? Anybody ever accidentally boiled off an entire pot of water at home? Yeah? Okay. I mean, it happens. You sometimes just forget about it. But that's why most kettles have the safety thing on them. Once it gets to boiling, it automatically shuts off because it makes a real mess of your pan if you do it. But it takes a long time. Like, you really have to forget, okay, that stuff is boiling and be gone for a long time, okay, before it's all completely gone. It takes a lot of energy. Now, if we're looking at, let's say we get rain for a couple of days, okay? We get rain for a couple of days. How much rain do you suppose falls? Yeah, probably a few centimeters. I mean, when we had all the flooding there in 2013, okay, in about a 2-week period, we got around 10 centimeters to 12 centimeters of rain. Okay, now that's spread over a geographic area that's several square kilometers. Okay, are we talking about a large amount of water? Yeah. Okay, I mean, we could do the math of it. We could go, okay, the bottom of our cube is this many kilometers square, and then cover that with 10 centimeters or 12 centimeters of water. We're talking about huge amounts of water. Okay, where did all the energy come from for that? Because it had to get turned into a vapor somewhere. Okay, the energy came from, well, yeah, the solar energy that hit the Earth, at least somewhere, probably at the equator. Okay, so we're talking about, that's why I keep mentioning this, it's huge amounts of energy, this latent heat that the jet stream can move around. Okay, it's huge, huge amounts of energy. Okay. All right, so melting or freezing, okay, latent heat of fusion for water, 333 joules per gram. Okay, if I want to calculate how much energy then is required, I use this formula right here. Okay, energy would be the mass of the water in grams multiplied by how much energy is needed for every gram, that 333 joules. Okay, that'll give me the energy required to do that job, okay, to melt that ice, or how much energy would be given off when the water freezes into ice. Okay, how many people have made ice cubes in the fridge before? Well, actually, you didn't make them in the fridge because they won't happen in the fridge. They'll happen in the freezer. See, no one caught me on that one. Okay, that's stupid. Anyway, okay, we know that energy has to be given off when water freezes because our fridge has to run. Okay, if you're making a lot of ice, like if you put a case of water, okay, in the freezer to freeze the bottles, if you're going somewhere and you want them to be cold for a long period of time, your fridge is going to run steady for several hours because of all the energy that it's going to have to absorb as that water freezes. Okay? It's quite a bit, actually. Right? Okay. So, yeah, like I said, the formula is E equals M times LF. Okay? This number here is LF. You will always be given that number in the same way that you'll always be given the specific heat capacities if you require them. All right? Good news? Even though this is a really easy formula, you will never have to use it in any other form other than this one. That is, you'll never have to manipulate it. We're always going to use it to calculate energy, okay, and nothing else. So E equals mass times the latent heat of fusion. Okay. And then conversely, when we get to this part of the graph right here, okay, we're dealing with the latent heat of vaporization. Sorry, I gave you the wrong number. It's 2,260. I said 2,760. I was wrong on that. Sorry. Okay, 2,260 joules per gram. Okay. Notice there's no degree Celsius in this one, right? Specific heat capacity is joules per gram degree Celsius, but this is just joules per gram. Why? Right? There's no temperature change while it's changing state. Okay? If you don't believe me, go home tonight, put a pot of water on the stove, heat it until it starts to boil, okay, with a thermometer in it. Once it starts boiling, it won't get any hotter. It'll stay at that temperature. Okay? It simply can't get hotter until the state changes. Right? We might have time on Tuesday, I'm hoping, to go into the lab and do an experiment with melting of ice. Okay? We'll melt the ice and we'll actually show that the temperature stays flat until all of the ice has actually melted. Okay? And then we'll see if we can get a number close to 333 for the latent heat of fusion. Okay? All right. Is this part making sense here? All right. Before I show you kind of the problem-solving part of this, I'm going to show you a cool video of what happens when you super cool water. Okay? Has anyone seen, like, if you put water in the freezer and it doesn't freeze, you've left it in there for like a day and a half, you pull it out and it's still liquid? Anyone ever had that? Okay? You ever flick the bottle? If you haven't, try it sometime. You need really clear water. Like, it's got to be bottled water. Can't have any bubbles in it or anything like that. Okay? Put it in the freezer, let it get really cold, and then pull it out carefully and flick it. It'll freeze like that. Like in the snap of a finger, it'll just go and freeze. Okay? Because you get it cold enough, but there isn't what's called a seed crystal or anything in there that can get the crystallization process going. If there isn't any of that in there, the water will stay liquid down to like a very extreme temperature. I had a chemistry prof, and this was the only thing I enjoyed about chemistry in university. We were doing something like this, and he brought in super cooled water. It was minus 35, this water. He brought it in, and he had like a little bit of salt. Okay? And he set this, he was like super careful about everything, because if he'd have jarred it at all, it would have just froze, right? He said, so I've got this really super cooled water. He had this container around it that had the liquid nitrogen in it so that it would stay cold, okay? And then he took a little bit of salt between his fingers and just went like this and dropped like a single grain of salt, and the thing just went psh, and it just popped, okay? And there was this instant freezing of the water. It was really, because at minus 35, it's going to freeze real fast, okay? When you put something in the freezer, it's going to be like minus 10 maybe, okay, when you do it. All right. I want to heat up ice that's initially at minus 15. I want to turn it into steam at 150 degrees, and I've got 250 grams of it. Okay, if we go back to our little graph there of the heating curve of water, okay, it has this shape. Okay, this line here is at 0 degrees Celsius. This line here is at 100 degrees Celsius. Okay, I'm starting where on this graph? Minus 15. So let's say bottom of the graph. All right, I'm starting down here. How many different stages are there in this process? Like if I start with ice, the first thing I've got to do when I start adding energy is that I've got to do what with the ice? Before that. It's not going to melt till it gets to 0. I've got to get it to 0. So I've got to heat up the ice. Okay? What kind of energy am I changing if I'm heating up the ice? Kinetic. That's this part of the graph. Okay? In this part of the graph, I'm going to use which formula? E equals mc delta T, because the temperature is changing. I know I got to use that formula anytime the line is going up, because anytime the line is going up, I've got a change in temperature. Everybody okay with that? All right. What formula am I going to use for this part here, where it's flat? Or what's happening there, where the line is flat? I'm still adding energy, and the ice is melting. Don't start doing the math yet, guys, because there's something that I haven't showed you yet. Okay? I've got to use this formula that tells me how much energy would be required to melt a certain mass of ice. And I do know the mass. Okay? All right. Once I melt all of the ice, and I've got liquid water at 0 degrees Celsius, if I keep adding heat, what's going to happen to the water? It's going to increase in temperature. What formula do I use to calculate how much energy would be required? mc delta T. Again, anywhere where the line is showing a change in temperature, I've got to use the formula that it calculates energy using change in temperature. All right, once I get that liquid water to 100 degrees Celsius, I have to use what formula to calculate how much energy would be required to vaporize it? Right, E equals mLV. Okay? Mass times the latent heat of vaporization. That is how much energy per gram is required to evaporate water. All right, once I'm done that, I'm right here. And now I have steam at 100 degrees Celsius. If I keep adding energy, I want to get it to 150 degrees. I've got to change its temperature again. What formula do I use? E equals mc delta T. Okay, so really, you got to remember, anywhere the line's diagonal, I use this formula because temperature is changing. I use F at the freezing point. I use V at the vaporization point. Okay? Sometimes things make sense. All right. Now, down here, I want to calculate the energy. I know I've got to use mass times C times delta T. I know the mass because they told me it's 250. What's C? What's the specific heat capacity? See, that's the trick. That's why I wanted you guys. Sorry, Kendi, I threw you under the bus there. Okay, ice has a different heat capacity than liquid water. So you got to look it up on your chart. The specific heat capacity of ice is 2.116 joules per gram degree Celsius. Okay, how much am I changing the temperature of the ice by? 15 degrees. That is probably the most common mistake that I see people make on a problem like this. They'll go 250 times 2.116 and then multiply it by the entire temperature change over the entire question. It's a very common mistake. But here's what we have to realize. I don't have ice up here, right? Ice doesn't exist here or here, okay? It only exists from minus 15 to 0 degrees Celsius. So I'm only changing the temperature of the ice by 15 degrees. Is everyone following me there? Okay. So times 15 degrees Celsius. Okay, so 250 times 2.116 times 15 degrees Celsius gives us 7,935 joules. Okay, so that's how much energy would be required to get the ice to its melting point of 0 degrees Celsius. Okay, so here, what do I use for M? 250, right? It doesn't change mass just because it's going from, or it's still ice actually at the beginning of this. Okay, so 250 times the latent heat of fusion, which we said before was 333 joules per gram. Hey, 83,250. Take a lot more energy to change state than change temperature. Way more. Okay, 83,250 joules. All right, now I've got liquid water at 0 degrees Celsius and I need to heat it to 100 degrees Celsius. What numbers am I plugging into this formula here? 250, okay? Just because I changed from ice to water doesn't mean I changed how much water I had. Okay? Changing state doesn't change the mass. It's the law of conservation of mass, right? Okay? I have the same number of particles that I had before. All right, 250 times specific heat capacity of water this time, 4.2, okay, times the change in temperature, which is how much? 100. I'm going from 0 to 100, right? I'm just heating the water from melting to boiling, okay? So 100 degrees. So 250 times 4.2 times 100. Okay, so 105,000 joules. Okay? It's a big number because it's a big temperature change. All right, now I have liquid water at 100 degrees Celsius. It's boiling, okay? I need to calculate how much energy is required to take it from liquid to vapor. Okay, so that's E equals MLV. Still 250? Yep. Okay, times LV, which is 2,260 joules per gram. Okay. Is this going to be a big number? Yes. 565,000 joules. Okay, now I have steam at 100 degrees Celsius, but I continue adding heat, so the steam's temperature continues to go up. So 250 times, what specific heat capacity do I use now? Steam, which is 2.02, I believe. Okay, and how much am I changing the temperature of the steam by? 50. Okay, a lot of times people will go 150, not thinking that they were already at 100. Okay, this is another common mistake, but I'm already at 100. I'm only going up another 50 degrees. Whoop. 250 times 2.02 times 50. All right, so it's another 25,250 joules. Okay, what do I do with all those numbers? Add them all up. Okay. So bottom was 7,935 plus 83,250 plus 105,000 plus 565,000 plus 25,250. 786,435 joules. Okay, so if you took a cup of water and put it in the freezer and froze it, and then put it in a pan on your stove and started heating it up, in order to make it disappear completely, would require that much energy. Okay, that is 786 kilojoules worth of energy. Okay, it's a fair amount. All right, you probably had a shower this morning. I'm not going to ask you if you did or not, but you probably did. Okay, when you get out of the shower, before you get a chance to towel off, how do you feel? Yeah, why do you feel cold? I mean, you just got out of a nice hot shower. It's not so much that the water's losing energy, it's that you are. Because what's the water doing? As soon as you get out of the, it's hot water, it's on your skin, and it's actually starting to evaporate. If you stood there long enough, you would be dry. Okay? You'd also be very cold, but you would be dry. Okay? And the reason you'd be dry is because the water would evaporate off of you. Where is it getting the energy from to do that? You. That's how sweat works. Okay? We don't just sweat so that we look cool. Okay? You're probably like, no, we don't. Okay? But we sweat because as we sweat, our body energy is used to evaporate the sweat. And that makes us feel cooler. Okay? Imagine you sweat out even 100 grams of water. If all of that evaporates, you've lost a lot of water, or a lot of energy. Okay? You've also lost some water, but okay, you've lost a lot of energy because it takes a lot of energy to evaporate all that sweat. Now, do you evaporate all the sweat that you sweat out? No. Okay? But you evaporate a good portion of it, unless you're one of those people that just sweats freakishly. Okay? Okay? There are some people who are like that, obviously. Guy who used to be the goaltender for the Edmonton Oilers, Nikolai Habibulin, okay? He actually had holes drilled in his skates because he sweats so much. You could actually, they caught it once on the goal cam. There was sweat dripping out of the holes in his skates. The guy loses like 10 pounds every game. Okay, he sweats out that much water. Okay, wearing those goalie pads. Okay? Every about 10 minutes or so, he skates to the bench and gets a new catcher and a new blocker, and the guys are just like wringing him out. It's disgusting. Okay, some people sweat like that. Okay, some people sweat excessively. It doesn't actually mean that they cool themselves any better. They just sweat a lot. Okay, we'll talk a little bit more about that tomorrow.